Which day is today? Today is the 1st of December, which means it's LiDAR Day at Optica. On the next hour, all together, we are going to design an FNCW LiDAR on photonic integrated circuit platform. What we're going to do together is to understand how we can benefit from the integration level of photonic integration and design an FNCW LiDAR on chip. And why an FNCW LiDAR on chip? Well, an FNCW LiDAR on chip will actually have many benefits compared to other direct detection of LiDAR. And those could be the improved range resolution, the improved dynamic range, the single photon sensitivity, so we no longer need high power to reach high distance, and also to measure the velocity. Photonic integration has evolved dramatically. And when you look at a coherent transceiver in Datacom Telecom, and you look at an FNCW LiDAR on chip, there are many similarities. Let's understand and leverage all the knowledge that we have in photonic integration to design live today, on the 1st of December, LiDAR Day at Optica, the first photonic integrated chip on LiDAR design live for you. And for that, I would like to give the floor to VPI Photonics, or key corporate member on Design Automation for Integrated Photonics and Optical Systems, Chris Maloney. Thank you very much for being with us today. The floor and the attention of everyone goes to VPI.
Yeah, thanks, Jose, for the nice introduction there. And thanks, everybody, for joining us and taking time out of your schedules for this OPTICA industry tutorial on automating the design of photonic integrated circuit, or PIC-based LiDAR systems. So today I'm joined by Dr. Nebras Deeb, who's an optical systems application specialist, and Eugene Sokolo, who's a principal application engineer. And I'm Chris Maloney, Director of Business Development at VPI Photonics. So the first question is, why LiDAR? Why are we talking about LiDAR, and why are we talking about it right now? So LiDAR technologies have been around for over 60 years. Historically, the main applications have been rangefinders, designators to find target an object, environmental applications such as wind sensing or sensing ozone, topographical mapping, and others as well. But the reason that we're talking about this right now is because autonomous driving is likely to be the first widespread commercial use for LiDAR. So the automotive LiDAR market is actually expected to double every year for the next 4 years, approximately. And in particular, Coherent LiDAR, which is why this is useful for autonomous driving, it can measure position, X and Y position, distance, and velocity. And that's the key point there. But it requires high volume manufacturing solution, and integrated photonics is one of the better candidates for this. Now, just to give a disclaimer, developing PIC-based LiDAR systems, it requires the right tools, experience, and know-how. I wouldn't claim that we're LiDAR experts in the room today, but we are experts in simulation, and we do have a wide range of experience in datacom telecom. And so we're leveraging our experience and know-how there and bringing it into LiDAR. And Eugene is actually, his expertise is in laser modeling and photonic integrated circuits as well. So just a very high level overview. I know there's a wide range of people in the room today, some with a lot of experience, some with almost none. So I'll just take you through this block diagram, the concept of LiDAR, how does it work? And then we'll get into more details as we go forward. But it first starts with a waveform generator. So this is an electrical sinusoid that drives your transmitter or your laser. And that laser goes through some optics or some beam steering so that you can actually scan an entire scene. And that laser will propagate through atmosphere or free space. There might be some weather conditions to consider there. And it will reflect off of a target. And it will reflect back through that atmosphere, back through free space, and get detected on the other side. Now the laser signal and the signal coming back to the detector will actually be mixed together. And what you'll get from that is a beat frequency. And essentially you're measuring the time of flight. And so that you can get the distance from your position to that target. There might also be some Doppler effect if that target is moving. And in that case, you can actually measure velocity as well. And then there's some digital signal processing and readout electronics as well, which we won't touch on today. So it seems like a pretty basic concept, but there are tons of things to consider, such as the type of system. Is it direct detect? Is it coherent? How are you actually imaging a scene? Are you using flash or scanning LiDAR? What are the weather conditions like? What wavelength are you using? The type of laser, is it a fiber laser or is it an integrated laser? DFB, DBR laser, is it a VCSEL? There's a lot of options there. And then there's the PIC design. So which material platform are you designing this on, and how are you laying out your design as well? So due to the diversity of all of those concepts, system configurations, technology choices, a design automation tool is really required to optimize and design your LiDAR system. And so that's what we're going to be focusing on today. So just to give a brief outline, I'm in the middle of some of the background information right now. The first section we'll be talking about is ranging. So we'll actually go through the design of an FMCW LiDAR system. So Nebraska will take us through that, show the behavior of it. And then Eugene will join us and talk about the PIC-based transmitter design. And he'll focus really on the laser and the non-linearity of the laser and how do we mitigate that in the system. And then we'll move on to beam steering, and we'll stay at the PIC level, the circuit level, and talk about an optical phased array for beam steering. And then we'll take it back to the system level and talk about simulating adverse weather conditions and how does that impact the imaging performance of an entire scene. And then we'll conclude. So just before we get into things, I'll just give a brief overview of VPI Photonics and who we are. We've been providing photonic design automation software for over 25 years. Our headquarters is in Berlin, Germany. Eugene, Nebraska, and I actually represent our US office. And the way that we like to describe our software as first is it's integrated. So today you'll be seeing how the circuit level, the photonic integrated circuit level, and the optical systems level of our software actually operate in the same user interface, same design environment. So it's very easy to have a hierarchical design and jump between the different levels and actually combine them in a single simulation. Our software is also interoperable with many third-party software tools. So if you have some custom MATLAB or Python scripts, it's very easy to do some co-simulation in the software. If you're looking to do some optical electrical co-simulation, we partner with Keysight, and our software can be called from Keysight ADS. And we also have some NG-SPICE capability built into the software as well. And lastly, we claim to be industry leading. So a lot of the work that we've done in preparing for this LiDAR tutorial today has come from industry feedback. So actually speaking with customers and people that are in the field, both from the datacom space as well as those focusing solely on automotive LiDAR. And we've built some of those common problems into the tutorial today that we'll take you through. So in this tutorial, we're going to be working in VPI Photonics Design Suite. And specifically, we're going to be focusing on two tools. One at the transmission design level. So this will be VPI Transmission Maker Optical Systems that Nebraska will be showing. And we'll also be moving down to the component design. So using VPI Component Maker Photonic Circuits. And it's pretty seamless. You might not even notice the difference between the two tools since they're in the same interface. One thing I'll point out is if you are looking to use a fiber laser for your LiDAR design, we also have a VPI Component Maker Fiber Optics to design fiber lasers or fiber amplifiers as well. But we won't be focusing on that today. We'll be focusing more on photonic circuits. And one thing in particular is that you should just keep in mind that if you're actually going to have something fabricated at a foundry, we support a number of foundry PDKs in our software. So you can have something to start from. So those components that are available at the foundry, we have models built directly into the software. Or, and this is becoming more common, you can create your own PDK directly in the software. So if you're going and doing runs at a specific foundry, you can keep the IP to yourself and actually create your own PDK in that case. And then just for completeness, we also have tools at higher and lower levels of abstraction. So link engineering, this would mainly be for designing optical fiber networks and device simulation. So if you're doing some waveguide or fiber design itself, but those are a little bit outside the scope of today's conversation. So just to give an introduction to VPI transmission maker optical systems, there's a wide variety of applications this can be used for. It's mainly used in the datacom telecom space, so for short reach or long haul DWDM systems. But we're getting more and more users using this for free space optics as well. So satellite communications has really been driving that lately, and now LiDAR. And so a lot of what we've developed for satellite communications, we can actually extend into LiDAR as well. So there's many things you can do, explore different modulation schemes with the software, explore different technology choices. You can see it's schematic-based design. And there's a pretty flexible analysis environment as well that you'll be seeing. So you can see a lot of eye diagrams and constellation diagrams here. And we've actually implemented some custom analysis for LiDAR for this example today. We'll also be focusing on VPI component maker photonic circuits, which includes a library of models and building blocks that include active components, signal processing elements, passive components. One of the key points here is that we actually combine time and frequency domain simulations together. So you can have a quick simulation, but still maintaining the accuracy that you need. And in particular, we'll be focusing a bit today on our active devices, so the laser, and they're based on photonics transmission line laser model, or photonics TLM model that Eugene will be describing today. Some of the key points of that is that it includes carrier dynamics, spatial hole burning, non-linearities, so current non-linearities, two-photon absorption, and it's bidirectional as well. So Eugene will be focusing a bit on that later on today, so stay tuned for that. And at this point, I'm going to turn things over. We can jump into the technical details. We'll actually get directly into the software, and I'm going to turn things over to Nebras. So Nebras, feel free to share your screen.
Thank you, Chris.
And the floor is yours now.
Thank you, Chris, and hello, everyone. My name is Nebras, and here I'm showing now the VPI Photonics Design Suite. This is the user interface. Let me move this a little bit. So you see here, we have several parts, and I'm going to focus on the system level. I'm going to start with part 1. So now I have the schematic open in the workspace, and this is built using our tool for designing optical systems. That's VPI Transmission Maker. And you see this represents this is the FMCW LiDAR system. I'm going to explain how it works. So here you see at the transmitter side, we want to do frequency modulation. So we have a laser source with a specific laser average power with a specific line width and a specific wavelength that's in the C band in this case, that's around 50 nanometers. We have these two modules which generate an electrical signal that has a triangular waveform, and we have this frequency modulator. This is an optical modulator. So this is driven by this triangular waveform, and it has also an input from the laser. So the optical signal then of the laser is modulated using this triangular waveform. Therefore, at the output of the modulator, we have a signal that is frequency modulated. So we have the chirp that's varying in a triangular waveform. Now, using this splitter, this signal is split. This represents a coupler. So it's split into two signals, the probe and the reference signal. And then the probe is taken so that the probe will go through a circulator and propagate through free space, hit the target, and come back. And then after that, it's going to be mixed with the reference signal here at this point with this coupler. And then balance detection is used. And here the thermal noise is considered as well as shot noise. At the output of the balanced photo detection, we have the an electrical signal here, and then we take the frequency of this signal and analyze it. So sorry, we take the spectrum and analyze it. So what we want to do is to find the peak frequency. What happens here is that the signal, when it propagates and hits the target and comes back, it will exhibit several things. It will have some attenuation. There is also a time delay, and there is maybe Doppler shift. So if you have if the target is moving, then we will have some Doppler shift. So there will be a beating frequency then in the spectrum that is the frequency of this beating frequency is proportional to the distance of the target. So we want to then detect the peak of that frequency. This will tell us how far the target is, and then using some mathematical expression, we can extract the distance. This peak frequency detector is based on uses co-simulation with Python. We can look inside, so we can look at the inputs. Here we have a Python script, so you can look at that. And it's very simple actually. What it does is taking that spectrum and trying to find the peak by doing some Gaussian fitting to the spectrum, and then it gives me the value of the frequency, and that's the beating frequency.
Nebras, just quick question here. This file that you are presenting, is it possible for the people in the audience to download and to use it as a template?
Yeah, they can. Well, if they have the software, like this demonstration is a part of the software, so they can basically access the code for this module here, and yeah, they can download it then.
So I'll just add one thing. If anyone's interested in evaluating the software, we'll put our contact information up at the end, and we'll make that available.
Okay. Yeah, thanks for this question. So let's now, in this case, so again, the target is located at a specific distance, and it can be fixed or we can sweep it. So I have here this sweep file, which is the distance. I'm going to open it. And what this does is going to use different values for the distance and apply that, and then we can visualize the results. So I'm going to run this. And so it's going to apply values of between 50 meters and 100 meters to the target distance. Please note that we are doing single shot in this example. So for every specific distance, we are doing one shot and detecting the signal and looking at the extracted distance. So the results show in the analyzer directly, as you see. So the first window here shows the driving signal as a triangular waveform. So this is an electrical signal. And this window here shows both the probe and reference signals together. What we are seeing is the frequency versus time. So this is the chirp evolution. And because we have different values, we can see here, we can navigate between them. So this is the results for 50 meters, and then we can show it for 60, 70, 80, 90, and 100. And as you see, because of the larger distance, then will result in a bigger delay. And so we see a bigger horizontal shift. And this is the reason why when we mix the two signals at the receiver, we find a frequency peak here, as we see, and the location is proportional to the target distance. Also, if there is a Doppler shift, we will see that this peak for the returning signal is higher than this peak because of the Doppler shift, and that will result in two peaks, as I will show promptly. So now, as I said, we are looking at the peak and then calculating the distance based on that, and we see these results. Then you see them here, and these, as you see, the distances are extracted in a pretty good accuracy here within a few centimeters. So these results were assumed that the target is not moving, and now I'm going to change the velocity and use a velocity of 40 meters per second instead of 0. We don't this. need this at this point, and then I'm going to run the simulation again, and we will see the effect of the Doppler shift in this case, as you see. So now, two things that we see. First, this is higher now, the frequency, as I said. So you see this, the peak here is higher than this one. This is on the other hand. This leads to a difference in the delay here, or in the horizontal shift between the waveform going up, the upward, and the downward. So there will be a little difference, and that leads to having two peaks here. Now, the distance between these two peaks in frequency, the frequency difference between them, will tell me how fast the object or the target is moving, as you see. So you can use markers and look at the frequency difference, and this, and then you can calculate then the velocity of the target. So in one shot, you can then find the velocity and the distance of the moving object, and this is the benefit of FMCW LiDAR systems. So one using this system like this, one can look at the different constraints, such as the line width of the laser. You have also the chirp rate. That's another constraint. Well, how far can the signal go in the given these parameters? You have a certain attenuation. We'll be looking more into these details, especially for the attenuation that the signal exhibits in part 4. So at this point, I would like then to pass the talk to Eugene, who will be talking about the other parts. So stay tuned.
Yeah, thanks a lot, Nebras, for this great overview of FMCW LiDAR system and its basic principles. Just to make sure, can you hear me all right?
We do.
Okay.
Yes.
Good. I'll start sharing my screen then. So once again, hi everyone. My name is Eugene Sokolo. I'm principal application engineer with main focus on the integrated photonics. And in my part of the tutorial, I'm going to talk about some of the constraints and opportunities which actually photonic integrated circuits bring to us on the example of FMCW LiDAR systems. And some of the constraints actually originate from the transmitter side and the behavior of our laser. And yeah, I'm going to discuss how a non-linearity of the laser actually impacts our LiDAR system. And that's the schematic Nebras was showing to you. And if you look into the laser model, it's actually quite simple. It's very high-level system level model described with very basic parameters such as line width, average power, and some polarization properties. However, that's not enough, right? It's ideal. It had this ideal frequency modulation as well. So everything is ideal, and we got these very nice pictures at the end. To dive deeper into the physics of operation of the devices, we need more accurate models. And here's another schematic in which we have the transmitter subsystem based on DBR laser, which is described in this paper here on the bottom. So you can check this design. And let's study how more accurate, more physical modeling of the laser actually impacts our system. So let me maybe elaborate a little bit on the design of this transmitter here. So it is based on DBR laser. So it has a front and back mirror to form the cavity. It has phase tuning for mode selection and tuning our frequency. Obviously, it has gain section for the stimulated emission, and it would also have some SOA, semiconductor optical amplifiers, and spot size converters or tapers to increase the output power from this laser. And actually, the models for the gain, for the phase, and for the SOA are based on so-called VPI for photonics TLM model. So that's one of the most advanced models we have in our integrated photonics tool. and it allows for modeling spectral effects, spectral dynamics of the laser, studying carrier and photon dynamics. It also includes non-linear effects, so two-photon absorption and Coherent non-linearity effects are included. You can specify your gain, your noise of the system, and so on. So it's really very advanced. It is bidirectional, so obviously in order to form the emission here, we need some reflections from the both mirrors. So it's bidirectional. It's spatially distributed, so spatial Hall-Burning effects are included, so we can actually see how and visualize how the carrier and photons densities are distributed along the cavity. So overall, it's pretty advanced model. Because of that, it takes a little longer. So maybe let me run the simulation right away and just continue talking. So first, we need to actually work on some particular parts, right? So in order to obtain the emission for a particular frequency, we actually need to align the reflectivity of this mirror. So I pre-ran this simulation. Let me visualize this. Okay, here's my simulation results. So, and it's not that easy to do, right? So you need to adjust you need to adjust the reflectivities, you need to adjust the phase shifts. So the whole work is done for these both two mirrors. And actually one of them is just a regular Bragg grating mirror, and another is sampled Bragg grating. So both are possible to simulate. And yeah, once we employ this in the system, and the system remains pretty much the same as Nebras was talking, so we split the signal, we obtain the probe signal, which travels through circulating free space, hits the target, reflected back, experiences some attenuation, some Doppler shift, and then it is combined in the splitter with a reference signal and detected by a balanced photodetector. And we can analyze the electrical spectrum. So let's take a look at the results. So they're still coming, but we can already see a few important peculiarities here. So in the first all, we apply again this triangular shape signal to drive our laser. And we can see that, yes, the frequency is tuned. However, if we take a look at the response, we see that it's not linear anymore, right? And the problem with that is that once we take a look at the electrical spectrum, we cannot detect the peak very well anymore, and therefore it leads to a huge error at the estimated distance. So yeah, it is very important that for FMCW LiDAR system, it is very important, it is crucial that our sweeping laser frequency is linear, it has linear response. So how could we achieve that? And we could achieve this by applying some pre-distortions. So let me activate this guy here and run the simulation again. And while it's running, I explain what it does. So the idea is that based on the response we just received, we could apply some pre-distortion. So we have some function here defined. I can open and show this function to you. So it's very simple, just polynomial function, which distorts our electrical signal. And actually, that's pretty a good technique. And you can also, once you get this example, you can play around. So you can define your own functions here, maybe call even third-party software using this technique. But in our case, yeah, it's a very simple function. And let's see how this pre-distortion actually impacts on our results. One thing actually I forgot to mention, which you might wonder about, is those transients which we can see. And those originate from from the physical behavior of the laser. And for sure, in the real system, you would like to avoid this, some of these transients or mode hopping. But in reality, you might see them. And the reason why I left them here in this example, just to show that, yes, these kind of effects are included into the laser model. So it could account for initial transients. It could account for mode hopping effects. And obviously, all of them have a drastic impact on your FMCW LiDAR system. In the first place, what we can see with this pre-distortion switched on, that our electrical signal, our driving signal, is not linear anymore. Let me take the drawing tool again. So we can see that it's not linear. On the other hand, if we take a look at our frequency response now, it is linear now. And we can see this in the detected electrical spectrum right away. So we can distinguish the peak very well, just perfectly fine, once again, and we can estimate the distance with high accuracy. So we can see that linearity of our laser system, of our transmitter, is very essential for FMCW systems, and this needs to be accounted for properly in the simulation if we want to study these effects and if we want to explore how those effects could be mitigated. Okay, let me continue going down the rabbit hole here and switch the gears a little bit.
So, Eugene, before
yes.
you continue, I would just like to say to everybody, feel free to put your questions in the Q&A box below, and we'll address those at the end. But yeah, continue, Eugene.
Yeah, thanks, Chris. So in all our previous discussions, we considered the distance to just one single point. And obviously, this doesn't give us a full picture of our surroundings. One would like to know if there is a person in front of us, or a car, or a building. And for this, we need to scan our beam in both horizontal and vertical directions to obtain the full picture. There are various solutions for that. I saw there was someone writing in the chat about MEMS, but I think the ones based on photonic integrated circuits and hybrid integration in particular really shine for beam steering applications. I'm surely biased because I deal with integrated photonics, but let's see at one of those solutions. Let me open another schematic. So recently, solid-state optical phased arrays beam steering techniques have been extensively studied, I would say, and we present one of the examples described in this picture, in this paper here. And it was actually experimentally studied and proved to be applicable for FMCW LiDAR systems. So this is a very relevant example, I think. And let me spend some time on explaining how it works. So there are two main physical effects going on here in this case. So one of them, let me start from the end, maybe from the simplest one, but most crucial one. One of them is based on this grating coupler here. So it's our main gradient element, and it radiates the light on different angles, depending on the light wavelength. So tuning the laser emission frequency or wavelength allows for steering in one direction. Let's call this vertical V direction, V angle for the vertical. We can see this picture here. So we can steer it in this direction, just applying these two surface gratings. The second direction, let's call it H for horizontal, comes from the optical phased arrays. First, the signal is split. So we have this our laser signal. It is split using this star coupler into a couple dozens of arms, and then they travel through the array of waveguides, and we can see this little guy, which is a graphical representation of 39 parallel waveguides. They're not identical though, so they have a varied length. So each next waveguide has a little larger length defined by this length element. And at the edge, so here at the edge, the light is emitted from these multiple surface gratings or grating couplers. And the waves from these elements, they start to interfere. But because of the different length we had in the array of waveguides, they have different phases here. And because of that, the angle, they actually multiply each other at particular angle. And this angle is defined by the phase shift which was accumulated in this array. So how do we change this difference, or how we can tailor this? So, well, one obvious thing is actually to change the length increment. It's not practical, obviously, right? You cannot change the length very easily on your circuit. Another pretty common is apply some, have some phase shifters in these arms, right, and apply some currents and vary the phase. It's a little bit hard to scale it, and you know, even for these around 40 arms, it becomes pretty cumbersome already. In this particular case, it is used the dispersion of the waveguides itself. And let me run this simulation as well and vary the wavelength. So hopefully it works with all VPNs and connections, so on. Okay. So what we have here, we sweep the wavelengths from 1525 nanometers to 1575. And let's see what happens in both directions. So we detect them. Let me open the simulation results. So in the first place, we can see that our peak intensity position with just varying the wavelengths varies in both horizontal and vertical direction. So again, from vertical, we could expect this kind of, right? Because we have this grating coupler to vary it. But what happens in the horizontal direction is exactly what I was mentioning. So we change the wavelengths, right? We change the wavelengths and we change the phase relations between our waveguides. And this allows for sweeping. There is one more thing here that once we reach the edge of our field of view, if we have it properly designed, we start sweeping from another direction again. And this should be designed, but this allows for varying our steer in the horizontal direction in pretty wide range. However, because our vertical and horizontal angles are related to each other, there are some gaps in our field of view which couldn't be covered. So how this could be resolved? And the method proposed in the paper is to use multiple inputs at the star coupler. And yeah, you see, if we apply the light into different ports, we could effectively shift our picture on different angles. Let me show you this by running simulation once again. So in the first place, we don't expect our vertical position to be varied because we fixed the frequency, we fixed the wavelength, so the vertical position doesn't change. But let's see what happens in the power distribution versus horizontal angle. So it's almost there. Okay, so that's what we see here. Our vertical angle, as I mentioned, doesn't depend, but our horizontal angle does depend on the port we applied our signal into. And again, if we design this properly, we can cover pretty much all the gaps we had in the previous case when we had just one single input port. I pre-run this simulation. I can just visualize the results right away. So here's the simulation results. So doing both frequency sweep and applying to different input ports in the star coupler, we can cover a pretty wide range of our field of view. So in horizontal direction, it's pretty actually large. It's like about 15 degrees. It's not that large in the vertical direction. It's just about 2-3 degrees, which has to do with design of grating coupler. So how to overcome this? Actually, different, I can close this. Different grating couplers could be used. So you can have multiple devices like that, multiple OPAs with slightly different grating periods. And what this allows to do, this allows to cover way broader and scale the range in the vertical direction. So here's another simulation result. So if we have multiple OPAs with slightly different grating periods for our grating couplers, we could cover, again, pretty much a broad range, about 13 degrees in vertical direction. So that's how the beam steering could be done. But obviously, that's not something which you would think of when you say about designing integrated photonics, because actual photonic circuits design implies for a layout of your chip and fabrication. So how could you do this, and how the software could be of any help here? So in the first place, okay, let me open another example. So in the first place, once you start fabricating your design and thinking of fabricating it, you need to think of a technology, and you think of a photonic foundry. So for this example, I'm going to use just demo fab, but you might use some other commercially available foundries, or actually you might come up with your own custom PDK. So what's PDKs? So PDK gives you, it's a library of predefined components on the simulation side, at least. Maybe I can show you the list of PDK. So it has some restricted set of modules. They have some models which reproduce the behavior of actual devices of the foundry, of actual devices fabricated at the foundry. It has very little parameters to control because the models are already incorporated inside, but it might have a few parameters to vary. Okay, and if you understand, so that's pretty large scale circuit, and creating it from scratch could be a tedious task. So what we can do, we can use some scripting capabilities. So what is done here, we just take a couple basic structures like waveguide, arcs, and grating couplers. And actually, you can also include your custom devices like this grating coupler in this case, and just play them and repeat as many times as you wish. So let me show how this works. So, and the good thing, you can customize it, you can redraw it, you can vary the parameters, and you can, again, use your custom components here, and this all automatically created. However, the fundamental difference from simulation perspective and between for photonic integrated circuits, fundamental peculiarity is that waveguide, they have this dual nature. So they not only connect our elements, but they also function elements. As you remember, the phase depends on the length of the waveguides. So in the simulation, it's very important to account for the proper length of our waveguides. That's why we came up with so-called layout-aware schematic-driven approach. So when in the circuit simulation, you actually invoke some layout information to get the proper length and shapes of the waveguides. So you can see, for example, here that we have so-called elastic connectors, and we have some port locations in the element. So already on the circuit schematic capture level, you could account for some actual physical locations of the devices on your chip. And you can use automatic routing using these elastic connectors. So they just connect these two elements automatically. So we can take a look at the top layout view for this circuit. So there is a top layout view. You can see that's already actual sizes of the devices. So there are some grating couplers here. So you can check here if the circuit is consistent, if there are any broken, and if there are any broken, it will be indicated on the circuit. Finally, in order to do the layout, you might want to export the circuit into your favorite layout tool, or even generate a GDS max. Let me do this real quick. So it invokes one of the layout tools, Natsuki Design in this particular case in the background. It gets information about the actual sizes of the waveguides and generates a GDS mask, which could be visualized in K-layout, for example. So obviously there are many things to study, and I'm looking forward to your questions. But now I would like to give the floor to Nebras again, and to show some how this beam scanning could be applied to real systems, to real images.
Thank you, Eugene. Very nice. Yeah, so I'm going to talk about the last part of the schematics that we show in the software. It focuses on weather conditions, and it's similar to the first part where I showed the. We are back into the system level. We have the system, but the difference now is that instead of doing one shot to measure the distance of that object, that is one distance, and we have one velocity. Now we want to imagine the case where you have a scene in front of the LiDAR module, and you want to, like this, you want to scan all the do scanning with beam steering, for example. You want then to measure all the distances for all the pixels. And also considering the weather conditions. So weather conditions are one constraint in a system like this for LiDAR systems in general. And you can imagine that if you have a lot of fog here, then maybe the LiDAR module will not be able to detect or see these far buildings, for example. Maybe it will be able to see only this sedan and this van. And this is what we are going to be looking at. So fortunately, I have some results already generated. So for the different cases, and we have this module of free space. So let me show you what this does. Mainly the signal is going through free space through this module, and this module is basically for free space communications, and it can consider I can show it here as well. So you can specify the link type, whether it's uplink or downlink for satellite communications or ground to ground. It considers scintillation effects, the atmospheric scintillations. You specify the beam length, beam launch radius, or the receiver aperture, and there is pretty much advanced modeling for the free space channel, as you see, considering the different effects. But it's also used here in this example for LiDAR. And in our example here, when you have more fog, for example, you would expect to have more attenuation. So this module will consider whether in this way you have some rain, you have some fog. So based on published literature, you can the attenuation then is calculated in this case. So what we are going to do here, we are doing beam steering. So I have this sweep, and I'm going to vary the X and Y. I'm going to be scanning the pixels here with certain steps, and then I'm going to be generating a figure. So remember this figure. So 2 cars, and please bear in mind that we have generated a depth map that corresponds to this figure, and then that's what is being used in the simulation. So so let's look at the results here. So I have here the result for when I have some fog. So I can still see that there is a kind of a sedan car here, and there is a van, And with thick fog, when I have more fog, then the details start to disappear. And I'm going to do one run for the case of when having even more fog. So the case of dense fog. So fortunately, we can use parallel simulation here. So in this case, it's going to take only 1 minute to finish. So now it's calculating the results for the last case. So the fog is expressed by the variable visibility in this case. So whether it's 200 meters, 40 meters, or 20 meters. Yeah, and by the way, there is a lot of literature that focuses, or research that focuses on this aspect, the weather conditions. You can look at that, and most of them are based on experimental work, where you have a big chamber, then you can generate some smoke or generate fog inside the chamber and look at the performance of the LiDAR system. So, but it can also be done in simulation, as you see here. So as you see, it's running. And we'll start to see the results soon here for this third case. So because we are doing parallel simulations, so it's going to stack the results from different simulations together. And this is the final results that you see here. So you can barely tell what's going on here, unlike the first two cases. So we have some fog, thick fog, and dense fog. And yeah, then one can explore this constraint, the weather conditions, by adding more fog, maybe looking at the effect of using a higher power of the laser, for example, or looking at the maybe using some digital signal processing at the receiver side, and so on. So this is what I wanted to show you for this part. And at this point, I'd like to pass the talk to Chris. Chris?
Great, yeah, thank you, Nebras. Yeah, that was, as you can tell, there's a lot of different types of analyses that you can perform. I'm just going to summarize things real quickly here, and then we'll get into the Q&A. But today what we did is we worked through our photonic design workflow, specifically component design and transmission design, all together in VPI Photonics Design Suite. And so some of the unique things with photonic circuits, as Eugene already showed you, you can work with a number of different foundries and use their building blocks directly in the software. And we also partner with a number of the different layout tool vendors as well. Now, one thing we didn't touch on, but you can do, is if you need to go into deeper levels of physics, we have VPI Device Designer, so you can design waveguides and fibers based on 3D beam propagation method. There's a number of different mode solvers in there as well. And on the other side, if you actually want to get into more electrical optical co-design, we also have this integration with Keysight ADS as well. So really, just to conclude, autonomous driving really requires this high volume manufacturing and cost-effective LiDAR solution. So integrated photonics seems like it's a great fit for that. But of course, as you've seen here, we're just opening up the can of worms here for the many challenges that are needed to be addressed. And also system level consideration is needed. So it's really not enough just to study the non-linearity of the laser, but you should really be studying how does it impact the overall system performance. And so VPI Photonics Design Suite really addresses a lot of those challenges in developing these systems. So we have this industry-leading photonic design automation software, so you can really study these physics-based impairments on your system. And we've also integrated the circuit and system-level approaches together, allowing for this hierarchical design. And then lastly, just interoperability for customization. It allows for customization and use for third-party software tools, and it really allows you to simplify the tape-out process at photonics foundries. So I know one of the questions that I've been seeing in the chat is that, is this FMCW LiDAR application example available? And so it is. If you're interested in using the software, please feel free, as part of this industry tutorial, feel free to reach out to us. We can schedule either a live demo of something you're interested in, or actually get in and actually do a software evaluation. So I've included both, the website, our sales information, and I put my personal email address on there as well. So feel free to reach out.
Always amazed, Chris, that how fast you go from the system level design to the layout design and back to system level. You look at the big picture and then you go back and you design the waveguide width and you go up. It is quite impressive. So tell us what's next? What do you want out of the people that will join the meeting today? What do you want them to do after this meeting?
Yeah, it'd be great to connect with as many of you as possible. I know there's great questions in the chat. And so what we've done so far is we've taken feedback from conversations with our partners and built some of those, some of that functionality directly into the software. So it'd be great to get more feedback from you guys here and women in the who are attending and build that and keep building upon this. And then if you guys are interested, if you're interested in evaluating the software, feel free to reach out to us. We can send you some download instructions. We can chat more, and you can actually get your hands on the software and run some of these simulations yourself.
So Chris, what I want out of this meeting is to have as many people as possible playing with the design that you showed today. As many as possible. Do that for me. I really want people to tweak the parameters of the FM square, to tweak the parameters of the free space link, to tweak a bit what they can do with different frequencies, with different range, to see what kind of velocity range they could measure, how fast could be a detector speed, and based on how much power or how little power we can put a light source. I want people to play with these parameters. This is how great cooperation starts. Chris, Eugene, Nebras, thank you so much for this tutorial. It was spectacular.
Yeah, thanks, Jose. And thanks everybody for your attention today. Appreciate it.
Thank you very much.
Yes,
Please stay tuned. In the OPTICA website, you have all the upcoming events. We love these industry tutorials, but most important, remember, the success is in the follow-up. So if you have any further questions, or you would like to make my wish come true and try this example, all you have to do is please contact VPI, contact Chris Maloney. My name is Jose Pozo, and together with Elise Friskage, we hope we made good use of the last 70 minutes of your time. Until the next time, stay OPTICA. See you soon. Bye-bye.